Alright, welcome. In this video I want to continue talking about graphs. In the last video I sort of did a quick introduction to graphs and I laid down a definition of what a graph is. And I also quickly outlined the two standard ways that you might implement a graph, either as a linked structure or as an underlying an array list or an array, but usually we describe it on an abstract level as a matrix, an adjacency matrix. In this video, I want to continue talking about graphs, but I want to focus more on some of the terminology that we use for graphs. So in this video, we're taking a little bit more discrete math sort of approach to the graph and looking at different words that we might define relative to the graph that makes it easier to talk about when we want to start talking about algorithms for graph-related problems. So the first definition is a definition I think I kind of brushed over last time, is what we call a simple graph. And so here I've got my example graph, which is a simple graph, is an undirected graph with no loops. So a loop, remember, is a self-edge, an edge that connects a vertex to itself, not what we call a cycle, which is sort of like a loop-like structure inside the graph, which I'll just talk more about in a moment or down the road here. But again, a loop is just a self-edge, and so this is an undirected graph, meaning no direction on my edges, or sometimes that's bidirectional. We think of the edge going both directions, and then no self-edges. So certainly this meets that criteria. We call this a simple graph, or sometimes just a graph. If we're not trying to be more specific, we might just say a graph when we mean a simple graph. But if we want to, emphasize that we mean indeed an undirected graph with no loops, we'll sometimes call that a simple graph. Okay, so now let's talk about some of the, again, terminology we use. So say we focus in on this vertex here, we say the degree of a vertex is going to be the number of edges incident on that vertex. So we've got 4 here, so the degree is 4. And alternatively, sort of an equivalent definition here, the degree could be defined as the number of vertices that are adjacent to the vertex. So 2 equivalent ways to define the degree of a vertex. And then we can also, if we focus on those adjacent vertices, we'll usually call that the neighborhood of a vertex. So here we've highlighted the neighborhood of our vertex. Okay, another sort of natural concept in a graph is a path. And this sort of is central to a lot of problems in a graph. Dijkstra's algorithm solves the very well-known problem, the shortest path problem, the shortest path between 2 points, which I sort of call these days the Google Maps problem, which is when you pop open your Google Maps, what you're trying to solve is you want to know the shortest path. So what is a path? Well, a path in a graph then is going to be a sequence of vertices. So here I've got them sort of highlighted in red. And here I'm just labeling them sort of agnostically, v1 up to vn. Say we have a path of length n. Or we might also say this is of length n minus 1, because that's how many edges would be involved in the path, depending if we're counting vertices or edges. And the criteria that we have for it to be a path is not just any old sequence of vertices picked at random or arbitrarily. It's one such that if you take any 2 adjacent values in our sequence, so v1, v2, v2, v3, if you take those 2, then that should be in the edge set. So here I've got a set of all such edges. These are the set of all the possible edges, v1 connecting to v2, v2 connecting to v3, all the way up to when I is less than n, so the last value of I would be n minus 1 to n. So this is just saying that the set of all edges connecting those vertices in the sequence. So I've highlighted those edges, of course, in red here as well. And usually we think of the path as being a sequence of vertices or a sequence of edges, and often it depends on why are we talking about the path? Maybe we're using it in a proof, so it might be useful to talk about the vertices, or if it in a different type of proof, it might be useful to talk about the edges. Or maybe it's an algorithm that we're using this path for, and again, for the purposes of the algorithm, maybe it's the vertices we care about, or maybe it's the edges. So there's not really one definition here that's going to work best, and in fact we could find an equivalent or parallel definition here relating edges, so a sequence of edges such that their endpoints sort of match up, right? And that kind of makes sense too. That would be alternative definition. It would also be an equivalent definition, meaning any path identified by this definition should be identified by that possible alternative definition. So we're safe to settle on this definition if we like. And so usually, at least I find, more often than not, I'm interested in the sequence of vertices, and this is just also a convenient way to define it. So it's a little easier to define a sequence of vertices with edges connecting them than a sequence of edges is with endpoints connecting them, I guess is a way to say that. At least I found it a little easier to define it this way. So in addition to a path, we can define what's called a simple path, and this is actually a simple path. A simple path is one that does not repeat any vertices. We could turn this into sort of a non-simple path by doing a loop-de-loop sort of somewhere in there. And if you do a loop-de-loop, then you'll have not a simple path because you'll have to repeat a few vertices more than once. All right, a cycle, and here we have a cycle. Sort of called it a loop-de-loop before, but that's not what we're talking about here. This is a cycle, which is a structure inside of a graph. And it's a path-like structure. And in fact, one way we can define a cycle is as a path that starts and ends at the same vertex. Now, that's sort of a loose, informal definition. It works in a lot of situations, but I want to be a little bit more formal in this situation. But because I said the cycle is a path, you'll notice that the first thing I do is I define it in the same way as a path. So a cycle is a sequence of vertices, v1 up to vn, satisfying the same definition of a path, except that it has an additional criteria, which is the last vertex, vn, is connected back up to the original vertex, v1. And that's sort of, maybe we can think of the path going like this, and then this is the additional vertex, or the additional edge, sorry, that connects us back to the beginning. So because of that, this is just sort of, it's a path-like structure, it's just an additional definition and criteria, but cycles play an important role, just like paths do, in a number of algorithms. Now, this is also an example of a simple cycle. A simple cycle does not repeat vertices. And just like I mentioned with the simple path, we could sort of turn this into a non-simple cycle if we added another sort of loop-de-loop or another cycle, if you will, over here. But when I do this, I'm forming sort of a figure-8 pattern, forcing me to double up on that middle vertex if I want to use all of them. So, so that would be a case where we would have a cycle but not a simple cycle. So I usually like to think of that figure-8 structure as a good example of that. All right, the next definition, this is actually a pretty important and critical definition. It's often assumed of our graphs before we apply an algorithm in a particular problem if there are certain outcomes that we're looking for. So this is a definition of what we call a connected graph. And in a connected graph, it's just a graph. Well, the definition of the graph here is a graph that has a path between any 2 points. But that's sort of, okay, I mean, you can kind of wrap your head around it and it kind of makes sense. But I think almost if we sort of reverse this, put this on its head, we could say a graph is disconnected if there are 2 points that do not have a path between them. Okay, and that makes things a little bit clearer. Looking at this graph, it's pretty clear that this one is connected, but this would be a disconnected graph. Then we can clearly find a couple points here that have no paths between them. In fact, this point right here is completely isolated. We in our disconnected graph here, we have what we call connected components. So I've colored each connected component separately here. The largest one I left blue. This one with 2 vertices I colored green, and then this one colored red is completely isolated, and we sometimes also call this an island vertex, one that is connected to no other vertices. In a graph, we can also have what we call a bridge. A bridge is any edge that if we were to remove that edge, it would disconnect a component. I guess this edge here is also a bridge. So again, another definition or alternative definition here is that a bridge is an edge that is not a part of any cycle. These ones here, these 3 for instance, are all part of this cycle, and so none of them are bridges. If we were to remove any one of them, then the other 2 would become bridges because we would have destroyed that cycle. All right, the vertices and edges that I have indicated in red here constitute a subgraph of the entire graph here. And so we can sort of define what a subgraph is more formally. It's actually very sort of straightforward to understand informally. So we have a graph G prime. We'll say that's the subgraph of another graph G. So the original graph is G, subgraph is G prime. As long as the vertex set of my subgraph is a subset of the original, and the edge set is a subset of the original. There's only one other criteria we have to make here, and then it's just sort of a common sense criteria that we would apply to any graph, but we're just applying it here because the first criteria does not necessarily imply it, which is that if you have any edge in the subgraph that you've created, its 2 endpoints also have to be in the subgraph that's created. So for instance, we can have this edge here, but we couldn't omit having this vertex as part of the subgraph as well. So basically just saying every edge has its endpoints in there as well. Now I have tried to highlight here that this subgraph is somewhat arbitrary. I just picked some vertices and some edges that satisfy this. You'll notice the way I've selected this subgraph, it's disconnected. This vertex here is isolated from the others. It's an island. And I haven't included all the edges I could have included for these vertices. If I did include all of the edges that I could have included for these vertices like this, then we say that the subgraph is induced by this vertex set. Okay, that's when we additionally, for any 2 vertices any 2 vertices that we do include in our subgraph, if the edge was in the original graph, then we'll include it in our subgraph. So the way we induce a subgraph of a graph is usually just by picking out the vertices and then bringing along all the edges that belong to those vertices. All right, a subgraph can have another property that we call spanning if the subgraph includes all the vertices of the original graph. So if v prime is equal to v. And this is a spanning subgraph is not as common as a spanning tree, something that we'll see in a future video, but that we will also see a little bit more of in this video. Now this graph here is not a spanning tree nor anything else other than it is a spanning subgraph because it includes all the vertices. Notice it's not even connected since this component over here is disconnected from this component over here. All right, all the definitions that I've discussed so far either apply only to undirected graphs because there's finer details when we try and apply them to directed graphs, or they apply to almost any type of graph whatsoever. So now I want to focus a little bit more on digraphs, directed graphs. Digraphs just another name for a directed graph. And so all I've done is I've added directions to my arrows down here, and I've done that somewhat arbitrarily, although not quite. I did it somewhat lazily actually. I just selected all of these arrows in my PowerPoint, and I just said put a end point on them, and so it was really the direction I drew them when I made this graph, and so it is somewhat arbitrary, the shape that has arrived, but it actually ends up having some interesting properties because I kind of drew the graph in this direction from the left to the right. Most of my arrows go in that direction. You'll notice only a couple of them go the other direction. And for the moment, the way I have it drawn, well, let's talk about some of the definitions that we can now apply here. Now, one thing we can talk about a vertex, we can still talk about its degree. We could still say the degree of this vertex is 4, but when we have a directed graph, we can now talk about the degree of edges coming in and the degree coming out. So these are what we call incoming edges, and the number of incoming edges is what we'll call the indegree, also known as fan-in. This is borrowed from circuits, where circuits are just one example of graph, where our nodes are circuits and our connections are just edges connecting the circuits together. And so looking at this particular vertex, we can quite clearly see that the indegree is 2. The out degree is also 2, which is also known as the fan out, which is just, again, the number of outgoing edges. So again, here defining what an outgoing edge is as well. What that means is in an undirected graph, you can have a couple properties that you can't necessarily have in an undirected graph. In an undirected graph, if you have a degree of 0, then you are an island, you're an isolated vertex. But when you're talking about a digraph now, in a directed graph, you could have an indegree that is 0 or an out degree that is 0. And if your indegree is 0, we will call these types of vertices sources, and that's when we're considering types of problems where we're maybe thinking of a flow of a resource through this graph, like these are some kind of pipes, or maybe they're network connections that we can send a certain amount of data down, and we're trying to get data from here to here, or water from here to there, or something like that. In those problems, we might think of this as the source, and then the alternative case, now I'm going to have to flip around this vertex to make this happen, but if I flip, or sorry, around this edge, if I flip it around, then this vertex here has a 0 out degree, and this is what we call a sink. This is sort of where everything sinks in. So we have sources and sinks. Now, in this graph that I've just drawn, and if I just go back a step, this has one source in this graph. There's no other vertex that has indegree 0. But a graph need not only have one source. There could be any number of sources, and in fact there could be 0 sources. This graph, as I've got it drawn right now, has 0 sinks. And the reason why I have flipped around this edge over here is because my most likely sink would be this one here, this vertex here, but I'd need to turn around this one exiting edge for it. So I turn it around, and that makes it a sink. So again, any graph, directed graph, digraph, could have 0 or more sources and 0 or more sinks. And again, this one had 0 until I flipped it around. But we could also have more, and it's quite easy to see. I could just add another vertex here and put an arrow to it, and put another vertex here, put an arrow to it. Any more vertices I add that just only have one arrow to them, or even I could add any number of arrows going to them, as long as they have no arrows exiting them, then they will be all sinks. Okay, so sources and sinks, useful concepts in a digraph. Now, the concepts that we've also applied to a regular graph, we can reapply here. So a directed graph directed path is just a path that contains directed edges now. The direction has to be going in that direction, so I've changed the set notation to ordered set notation, saying that it has to be in this order. Okay, but otherwise the definition is the same. Same thing with a cycle. Okay, the only, again, change is I've changed it to a directed edge now, so that we need to make sure that the arrows go in that direction. And it turns out, actually, if you look at all the cycles that exist in this undirected graph, if we ignore the arrows for a second, we blur our eyes, there's lots and lots of cycles, but this is the only one I could find. I don't think there are any others that actually existed in the graph that I had drawn, okay, because this is the only directed cycle. All right, all the undirected cycles don't don't go in a cycle. They all sort of end up going in one direction. They're flowing kind of left to right, most of my arrows. I looked at this one here. This one has potential. It's going backwards at least, right? Most of my arrows are going to the right. This one's going backwards, but this is its best option, I think, right here. Or maybe this one here, but it doesn't work. So no cycle with that one. So, but we do have a cycle here, directed cycle, that is. Now, using that idea, we can talk about the notion of connectedness as well. Now remember, connected was if there existed a path from every vertex to every other vertex. Now, to be what we'll now call strongly connected, you need to have a path from every directed path from every vertex to every other vertex. This is just not true of this graph. This graph is not strongly connected because it flows from the left to the right for the most part. Almost no vertices have a path to and from. Most pairs of vertices have a path in one direction, but not the other. Only the three in this cycle that we had here satisfy the definition of being strongly connected. That subgraph is. The rest of it is not. However, we can still say that this graph is weakly connected. And we say it's weakly connected if basically, if you blur your eyes, you don't look at any of the arrows, and it's connected, then it's weakly connected. Okay, so I sometimes talk about the underlying undirected graph. So chop off all the arrows and then check if it's connected. If so, it's weakly. So this graph is weakly connected. All right, so the graph that I had was almost a special graph. But because of this one cycle we found in it, it doesn't have a second property, and that is being acyclic. So I corrected this cycle by, again, reversing this black edge. And by doing that, I've now created the graph, I've turned the graph into a directed acyclic graph. And actually, at the moment, we might say, okay, well, that's exciting. What's a directed acyclic graph? Well, a directed acyclic graph actually has lots of interesting applications in computer science and to algorithms. And it's an interesting sort of sub data structure of the graph data structure, primarily because in some sense it's a little bit of a generalization of a tree that allows you to branch back together again. Okay, where a normal tree you have to branch out all the way down. There's no possibility for merging two branches back together again. But a directed acyclic graph says you can merge the branches back together again, as long as you generally are moving down the tree. There's no branches allowed, there's no arrows allowed to go backwards, because if they go backwards, you'll create the cycle. Okay. Now again, here it looks like this edge goes backwards, but actually if we drag this vertex over here and maybe drag these other ones over to just make room for it, we'll see that actually all the edges that we have to it are really kind of pointing left to right. This one's only going right to left because we've kind of drawn this vertex in the wrong rank. It should be further down this path. Okay. Now, again, one of the reasons this is interesting is because it does model some things. Now, sort of an interesting sort of side tale. Now, we usually inspire trees. If you looked at one of my earlier videos, we inspire trees from the notion of a family tree. Well, it turns out that most family trees are not actually trees, especially if you go back far enough, because it's likely that some branches blend together, and this is certainly true in royal family trees, where second cousins or cousins are more commonly to intermarry, and certainly in certain cultures that is more common than in others. And so this type of blending of your family will mean that you don't actually have a tree structure. You have a directed acyclic graph structure. And actually this was an interesting sort of bug, if you will, that underlied some of the early ancestry software. People were trying to enter their ancestry and they said, well, you can't do that, that doesn't form a tree. And I said, you should have told my great-grandma that, or something like that, right? Anyways, that's one of the interesting applications of a directed acyclic graph. And there are certainly many other ones. One is useful for just scheduling tasks. And another interesting thing is that we sometimes will sort of sort these to give us if this is sort of an order of dependent tasks, we have to do this one before we can do any of these four and so on. What order should we do all the tasks? Well, there's something we call a topological sort of a directed acyclic graph, which just gives us a nice order to solve them in. Okay, so continuing, another sort of definition that becomes useful is of a multigraph. In a normal graph, all the simple definitions we've considered only allow one edge between any two vertices. However, if this is mapping some kind of real world environment, maybe these are roads or something connecting cities, well, there might be more than one. In the real world, we're not trying to satisfy some mathematical definition. So that means we just need to stretch our mathematical definition. Instead of having just a normal graph where we only allow one edge, well, let's have a multigraph then where we allow more than one edge for any particular pair of vertices. Now, of course, I want us to think of a directed graph as sort of maybe being a special kind of multigraph. When we add directions on here, we can have a direction. We're allowed to have two edges between two vertices, one going one direction, one going the other. But a multigraph is saying now we could have any number of edges, not just the special case of a directed graph. Another definition that might be useful for a graph is called a planar graph. A planar graph is one that you can draw in a plane or in 2 dimensions like we have here, where none of our edges cross over, and that's the case for this graph. So this is a planar graph. Planar graphs are actually kind of rare if you just sort of randomly plunk down a graph. It's unlikely to be a planar graph, and that's because we can think of these as actually being 2-dimensional structures. Okay, and 2-dimensional structures trees are another 2-dimensional structure, but our graph in general can have any dimension. So if you think of it, just think about drawing a cube for a second. You can think of that as a graph, each of the corners being a point, each of the edges being an edge. And that graph is a 3-dimensional graph. In the real world, you can look at it, it's 3 dimensions. But drawing it, there's no way to draw it 2-dimensionally without crossing over our edges. So it wouldn't satisfy this definition. It wouldn't be a planar graph, and in fact, it's a 3-dimensional graph. We can draw it in 3 dimensions without crossing over any lines, but we can't draw it in 2 dimensions. Now, there, of course, are more dimensions than that. We could go to 4 dimensions. If you know what a hypercube is, if you know what a tesseract is, and I don't mean the cube from Avengers, a tesseract is a 4-dimensional cube, and you can think of it as being a cube in time, if you like, that sort of shifts in time. Or it has you can't visualize it. It can't be drawn in three dimensions without having the same sort of overlapping phenomena that you would have in 2 dimensions. But if you could look into 4 dimensions, if you were a 4-dimensional being, you could look at what a hypercube or a tesseract looked at in 4 dimensions. And of course, if you were a 4-dimensional creature, then we could say, well, there's a 5-dimensional cube or a 6-dimensional cube or a 19-dimensional cube. And so graphs can show you what all those types of cubes look like, and all other kinds of k-dimensional shapes that you want to as well. Of course, if you're a human like me, then you're probably restricted to 2 or 3 dimensions like I am. If you live in time, then maybe you can use that as your 4th dimension, but trying to visualize beyond that is kind of hard for me. But guess what? I have a tool that can do that for me. I have a graph, and I can maybe draw it and go take a closer look at it. Okay, so I talked a little bit earlier about how a tree is sort of a type of graph. Well, here I can maybe more precisely define what it is. It's going to be a connected, undirected graph with no cycles. I took out all the cycles here. I deleted arbitrary edges that were in cycles until no cycles existed. And that left me with a tree. And in fact, that strategy left me with something special. It left me with something we call a spanning tree. A spanning tree is a tree That includes all the vertices of the original graph. Okay, why is that? Well, remember we defined what a spanning subgraph was before. This tree that I've created is indeed a spanning subgraph. That is also a tree, right? It is also a tree because it is a connected undirected graph with the critical bit here being no cycles. Connected meaning it's not split into different chunks, right? But the no cycles bit is really the sort of critical bit of the tree. All trees are connected, but this one has also got no cycles. If we do split it into chunks, so I just deleted out a couple more edges here, but if you do that, then you're left with what we might call a forest, and this would be a spanning forest, which includes all the original vertices. But a forest, of course, is just a collection of trees. So we had a single tree before, which also technically counts as a forest, but this is now, we've got 3 trees that span the original graph. And you usually get spanning forests when the original graph was not connected to begin with. So you grab a spanning tree of each of the connected components, and that gives you a spanning forest. But for this example, I just arbitrarily deleted a few more edges. All right, the final type of graph that I want to look at is actually kind of an important kind of graph. This is a graph family, if you like. This is a family of what I might call complete graphs. A complete graph is a graph that has every possible edge. So again, here we're considering only two things. We're considering a finite graph. That's one thing I really haven't defined here. A finite graph is one that has a finite number of vertices. So you could have an infinite graph, and if you had an infinite graph that had an infinite number of vertices, then of course you would end up having an infinite number of edges. Well, that's a lot. If you also had a multi-graph that had no upper limit on the number of edges between vertices, then you could have infinite edges, and that's a lot. So here we're probably talking about finite graphs and not multi-graphs. But if you're talking about a finite graph that is not a multi-graph, then a complete graph has every possible edge. Or a sort of more precise way of saying that is between any 2 vertices there is an edge. Okay. And so here I've got actually my family of graphs. This is a family, I've only put the first, I guess technically I've got the first 6 entries here because the first entry is of size 0 and so it's invisible. You don't see it over here. The complete graph of size 0 has no vertices and no edges. It's the empty graph. And just like the empty set, it sort of just plays a special role in graph theory. It starts out as sort of the base case of a lot of proofs and so on, but other than that, it's not very interesting. This is also not really a very interesting graph. This is I sometimes call this a degenerate graph. It doesn't really have all the graph properties because it doesn't have any edges. It's just an isolated island. But this is a complete graph of size 1. It has all the possible edges. Now, if you had a graph that allowed loops, allowed self-edges, then the complete graph of size 1 has a loop on it. Now, you could turn all of these into a complete graph with loops by just putting loops on every vertex. Now, that 1 makes it messy, and 2 is not usually the standard type of graph that we're looking at, so I've not included them here. So this would be a complete graph of size 2, 1 edge, complete graph of size 3, 3 edges, a complete graph of size 4, which has, let's see, 1, 2, 3, 4, 5, 6 edges. Okay. Now, an interesting thing about the complete graph of size 4, we obviously just had, this is not really a degenerate graph over here, but it is kind of a very simple one with only 1 edge. This is a kind of a triangle graph, the smallest cycle, if you will. And this graph is special too. The way I've drawn it, you'll notice it has crossed over lines. Okay, has crossed over lines, edges. And what that means is, at least the way I've drawn it, it's not planar, but this actually is a planar graph. The way I've drawn it does not take advantage of that. The way I could have drawn it is instead, say I take this graph and I draw a circle in the middle and I connect it to my other 3, then we end up with a graph with the same shape as this graph over here, just drawn differently. And when we say same shape, we say isomorphic. That's Greek, meaning iso meaning same, and morphic meaning shape. So isomorphic, same shape. And so in graph theory, we usually will consider two graphs to be the same graph if they are isomorphic, even if we've drawn them differently. So we could have drawn this one sort of vertically instead of horizontal. It's still the same graph. So again, this graph here is isomorphic, at least, to another graph where none of our edges are crossing over by moving, say, this vertex inside this triangle here. Now, that's true of this graph, but it is not true of this graph, our complete graph of size 5. Our complete graph of size 5 cannot be drawn in 2 dimensions without there being crossing over lines. And so go ahead and try, move things around, flip one over here, one over there, in the same way we did over here. You'll never end up in a case without them being crossed over. So for instance, we could try and take this one and put it in the middle in the same way. It might uncross, these 2 lines, but it's likely to create some more crossovers somewhere else. So again, try and, or at least even if you are able to eliminate 1 or 2 of the crossovers here, this is sort of the standard way to draw it. You're never going to be able to eliminate all the crossovers, and so as a result, this graph we would say is not planar. And there's actually there are a few properties, or there are a few theorems that have been proven related to these properties. And maybe when we get through a few more definitions and talk a little bit about graph problems, I'll talk about how we can sort of tell by looking at the graph, if it's a complete graph, if it's going to be planar or not. Well, for complete graphs, that's quite easy. If it's of size 4 or smaller, it's planar. If it's size 5 or greater, it's not. And I stopped at size 5 here, mostly because I got tired of drawing edges, but a hexagon then, with all the edges in it, you can imagine what that is. It's sort of a hexagon with a couple of crossing over lines as well. And then next up, you could go take 7 vertices. And usually once we get to 5, I did it for 4 as well, but once we get to 5, we sort of just draw them all in a circle and just draw all possible lines. So after about 10, it just starts looking like a big tangled ball of vertices with all possible crossing over lines. All right, so that's a complete graph. All right, so that's just what a complete graph is. It also sort of given us our first idea of what a family of graphs are that we can define of different sizes using just sort of a formula, in the same way that you could define a family of sets using a formula as well. And so I want to end this video here. This video was primarily a list through of terminology, plus a couple different introduction to a couple different kinds of graphs that maybe we didn't look at in the last video. Please come back to this video if you want to just review your terminology. Otherwise, in my next video, I do want to take a look at techniques for traversing a graph, standard techniques for traversing a graph, with a little quick analysis of the runtime. So thanks again for watching, and stay tuned for the next video.